Hi, I'm Alvin, a research scientist at Apple, and today I'm presenting Unconstrained Channel Pruning. I'll start with the problem statement. Pruning is hard. As we'll show in a second, pruning sacrifices latency or accuracy. Here's option number 1. We can prune any channel we want, but add latency. Say we have X, a feature map with 4 channels. This is produced by operation A. For simplicity, instead of saying which channels each operation prunes, I'll refer to channels each operation retains. Here, operation B retains channels 0 and 2. Operation C retains channels 1 and 3. To give each operation the channels it needs, we make memory copies at inference time. These memory copies are expensive, sometimes making the pruned model even slower than the original unpruned model. We also have option number 2. We prune the same channels but lose accuracy. This is the option that most papers by convention take. Here is a feature map with 4 channels again. This time, operations B and C both retain channels 0 and 2. As a result, before inference, we can drop operation A's channels. This produces a new pruned operation A'. Then we can simply use A''s output twice, no copies needed. Since there are no copies, latency decreases, but because there are constraints, accuracy decreases too. So in summary, add latency or lose accuracy. Fortunately, we have a solution, and here's the intuition. Start again with the feature map X. Remove constraints so operations B and C can prune any channel. This preserves accuracy. Before inference, we then reorder weights in operation A. This produces a new operation, A', which outputs Y. During inference, we simply take slices of Y. Contiguous slices are free latency-wise, so this helps our pruned model reduce latency. In short, our insight is to not copy. Instead, reorder weights in advance and slice channels at inference time. This way, we reduce latency and retain accuracy. Here's now how to reorder weights. First, segment the network. Specifically, find subsets of the model that can be pruned independently of other subsets. Here's an example. A, B, C, and D are all convolutions. Segment number 1 includes A and C's outputs and B and D's inputs. The other segment, segment number 2, includes B's outputs and C's inputs. Since the number of input and output channels is completely independent, you can prune each segment on its own without affecting other segments. This reduces our problem to just pruning a single segment at a time. Next, convert the segment into a graph. Start with the segment that we just talked about. We have a single producer A on the left producing outputs. We have 3 consumers on the right consuming inputs. The numbers representing channels each consumer retains. For example, D retains channels 0, 3, and 4. Draw one node for every consumer, along with their channels. Add an edge if 2 nodes share a channel. For example, D and E share channel 0. This is our graph. For each node, the reward is the number of channels. For example, B retains channels 1 and 3, so it has a reward of 2. For each edge, the reward is negative the number of shared channels. These are our rewards. Next, find a path that maximizes those rewards. To be specific, find the maximum reward acyclic path. Since there's no cycle, our path can't include all 3 nodes. As a result, DE is our first path. There's only 1 node left, so B is our next maximum reward acyclic path. Using this path, we then determine a channel order. Simply read the path from left to right. Start with channels unique to D. Add channels shared by D and E. Add channels unique to E. Channels shared by E and B. Finally, channels unique to B. This completes our channel ordering. We then reorder all channels in this segment to match this ordering. In summary, here's our pipeline. Find a segment. From your segment, construct a graph. In your graph, find a path. Finally, use that path to reorder weights in the original model. Let's see some results. First, removing constraints improves accuracy. Here we compute the difference between unconstrained and constrained ImageNet top 1 accuracy for post-training pruned models. Positive numbers mean that unconstrained accuracy is higher. As you can see, the larger the model and the more complex the model, the more that unconstrained pruning helps. Next, reordering channels lowers latency. In this figure, we benchmark MobileNet v3 inference latency. Along the x-axis, we have parameter sparsity level. On the y-axis, we have GPU latency. We want lower latency, so we want to be lower on this graph. The dotted line is a baseline unconstrained export, whereas the solid line is the latency for ours. In short, our exported models are significantly faster than the baselines. You can install our unconstrained pruning export upscale using this pip command. And that's it. You can email me at alvin1@apple.com, reach out to me via my Twitter handle here, or find our open sourced export algorithm and experiments. Thanks for watching.